An agent that can't remember is basically a stateless API wrapper. It looks clever for one prompt, but it can't build up knowledge, it can't improve over time, and it definitely can't behave like a real teammate. Most developers feel this pain as soon as they try to reuse an agent across multiple sessions. The agent forgets every preference, every decision, and every lesson it should have learned. In this video, we are going to treat memory as a first-class design problem, not as afterthought. We will break down short-term memory, long-term memory, vector-based recall, knowledge graphs, and how they map to episodic versus declarative memory in agents. Then, we will implement a CrewAI setup where the Crew actually learns across runs using built-in memory and knowledge sources, and we will finish with concrete pitfalls so you don't ship an agent that quietly forgets everything. Most memory implementations look like this. You lock conversation messages into a vector store, call it track, and hope retrieval magically makes the agent smarter. There are three big issues with that pattern. First, you treat chat history as long-term memory. It isn't. It's just raw logs full of noise, duplication, and transient details that shouldn't live forever. Second, you never separate episodic information, what happened in this session, from declarative knowledge that are facts that the agent should know for all future work. So the system doesn't know what to keep, what to compress, and what to discard. Third, there's no persistent strategy. What exactly gets stored? When do you promote something to long-term memory? When do you forget it? Without explicit answers to those questions, your memory layer gets slower, more confused, and less useful as time goes on. That's why a lot of memory-enabled agents feel worse after a few weeks than they did on day one. Let's fix that by agreeing on a simple mental model for agent memory. Short-term memory is your working buffer. It captures the recent interactions, intermediate results, and local context that matter while the agent is currently executing. It should be cheap to update and cheap to forget. Long-term memory is what survives beyond a single run. Distilled outcomes, decisions, and lessons learned. You should only promote information here once it has been summarized and is likely to be useful later. Knowledge is different again. It's structured, relatively stable information about the world or about the user. Documentation, constraints, user profiles, and domain rules. This is your declarative backbone. Vector-based recall is just the access pattern on top. We embed chunks from short-term memory, long-term memory, and knowledge, and then pull back the most relevant slices into the agent's context window. Episodic memory mostly lives in the long-term traces of what happened. Previous sessions, past tasks, historical outcomes. Declarative memory lives in the knowledge layer, things that should be true regardless of the current episode. If you design with that separation in mind, your agent's behavior becomes far more predictable. Now let's map that conceptual model into a concrete CrewAI architecture. When you initialize a Crew with memory equals true, CrewAI wires up a memory stack for you. Short-term memory for per run context, long-term memory for persisted outcomes, and entity memory for tracking specific people or objects across runs. You get a structured place to store both episodic traces and distilled summaries. On top of that, you can attach knowledge sources. These might be string-based profiles, documentation files, or an external knowledge base. Those sources act as your declarative layer, stable facts the Crew can always query independent of any specific episode. For more sophisticated setups, you can point the system at external memory or graph backends that maintain richer structures like semantic graphs or cross-agent histories. That's useful when multiple agents or multiple crews need to share a single, evolving memory. The important part is this. Short-term memory, long-term memory, and knowledge are separate layers, and CrewAI already encodes that separation. Our job is to design agents and tasks so each layer is used on purpose and not by accident. Let's make this tangible with a small, focused example. A Crew that learns your learning preferences over time. We'll have two agents. The first is a preference researcher. Its job is episodic. Interview you about what you want to learn right now, ask a couple of follow-up questions, and then write a concise, structured summary of your goals and constraints. That summary is what we promote into long-term memory. The second agent is a learning planner. Its job is declarative. Read the stored summaries from long-term memory, combine them with a stable user profile in a knowledge source, and generate your next learning sessions. In other words, the first agent turns raw episodes into reusable traces. The second agent consumes those traces as input knowledge. Short-term memory helps both agents within the current run. Long-term memory lets future runs build on what you have already told the system. And the knowledge sources anchors everything with your stable background. This pattern generalizes directly to customer profiles, project histories, infrastructure changes, anywhere you want agents to accumulate and reuse experience. Now let's switch into the editor and implement this step by step. I walk through every command and every file so you can follow along and adapt this pattern to your own agent. First, let's set up a clean project for this demo. Let's open our terminal and create a new folder called Crew Memory Demo. Let's go into it. Next, we create a virtual environment. This will keep dependencies nice and separated. And let's activate that virtual environment. Once the environment is activated, any packages you install will be isolated to this virtual environment folder inside the project. Now it's time to install the necessary dependencies. This command will pull in CrewAI with its tool bundle plus python.env so we can load our .env file and load the environment variables inside of it. When the dependencies are installed, it's time to create a new file called .env. Here we will configure our model and our API key. You need to replace this part with your actual OpenAI compatible API key. You can also switch the model name later to whatever model you're using, as long as CrewAI supports it. But in my opinion, GPT-4o Mini is good enough for this project. Now we will create a single Python file that defines the entire Crew memory configuration and the CLI interface. Let's make a new file and call it main.py. And now we will build the application piece by piece. At the top, we import the standard OS module and path from pathlib so we can work with file paths. We also import world.env so we can load environment variables from the .env file. Then we bring in agent, task, crew and process from CrewAI. These are the core building blocks for defining agents, tasks and how they execute. Finally, we import string knowledge source, which lets us create a simple knowledge source from a string. We will use this to encode the user profile as declarative knowledge. Next, we call world.env, so the env file is loaded into the process environment. We define project root as the current working directory using path.cwd. This is a directory where we want CrewAI to store its memory and knowledge. Then we set the CrewAI storage dir environment variable using os.environment.setDefault. That tells CrewAI to store its memory files directly in this project directory instead of some global path. Finally, we read OpenAI model from the environment and default to GPT-4o Mini if nothing is set. To make the behavior visible, we define a function called showMemoryStorageLocation. This function reads CrewAI storage directory, falls back to project root if it's not set, and prints the directory. This is where CrewAI will store short-term memory, long-term memory, and knowledge files. We also define one more function, which is called savePlan to Markdown. It takes the original user query, the final result from the crew, and an optional file name. We build a path in the current directory, construct a simple markdown header that includes the user query, then write the header plus the result string into learningplan.md. At the end, we print the path so you can open the file immediately after a run. This makes the crew's output persistent, human readable, and easy to version control. Next, we define a function called buildCrew. First, we start by defining a string that represents the user's profile. This is our declarative layer. It encodes stable facts like their background, interests, and preferred learning style. We wrap it in a string knowledge source, trimming the white space and attaching simple metadata so we can trace where it came from. CrewAI will chunk and embed this behind the scenes so the agents can query it. Next, we're going to define two agents. The first one is the preference researcher. The preference researcher agent has a clear role and a goal. It builds a structured model of the user's preferences over time. The backstory tells the model that this agent interviews developers and produces reusable summaries. The next agent is the learning planner. The learning planner has a complementary role. Its goal is to design the next learning steps by combining stored preferences history with the user profile knowledge. Its backstory positions it as a learning architect for software engineers. We also set allow delegations to false for both agents in order to keep things simple. We also set verbose to true so you can see what you're doing in the console. Both agents use the model defined in OpenAI model. Next, we're going to define two tasks. The first is the collect preferences task, which tells the preference researcher to interview the user based on the user query we will pass at runtime. It explicitly asks for a short, structured summary focusing on topics, depth, time per week, and learning style. The expected output makes it clear this summary should be suitable for long-term storage. The second task is the learning plan task, which tells the learning planner to use all available memory and knowledge to design the next 3 planning sessions. The next task is the learning plan task, which tells the learning planner to use all available memory and knowledge to design the next 3 learning sessions. Each session must have a title, an objective, and a short description of hands-on work. The expected output is a simple numbered list. By being explicit in these descriptions, we make it easier for CrewAI's memory system to store something meaningful instead of raw, messy walks. And finally, we assemble the crew. We pass in the 2 agents and the 2 tasks, and we set the process to sequential. So the tasks run in order. First collect preferences and then build the learning plan. The critical flag is memory equals true. That turns on CrewAI's built-in short-term, long-term, and entity memory stacks. We also attach knowledge sources and pass in the user profile knowledge. That gives the Crew a persistent declarative knowledge base about the user from the very first run. Then we return the configured Crew. The final function that we're going to define is the main function. First, it prints a simple header and then it calls show memory storage location so you can see exactly where CrewAI will store its memory. You should see the current directory printed here. We then prompt the user with describe what you want to learn about AI agents. Whatever you type becomes the user query. If the input is empty, we exit early. We build the crew by calling build crew, then print a message to show that the crew is running with memory enabled. We call crew.kickoff with inputs user query, so both tasks can interpolate the user's request into their description. The result is the final output from the crew, the learning plan from the planner agent. We print the final learning plan to the console and then we call save plan to markdown to write the same plan into learningplan.md in the current directory, together with the original query. The if name equals main block just makes sure that main function runs when you execute this file directly. Now let's run it and see it in action. Open your terminal and make sure that you're inside the Crew memory demo folder with the virtual environment activated. Then you need to run python main.py. The script prints the memory and knowledge storage path. This should be your current project directory because we set CrewAI storage dir to path current working directory. Then it will prompt you to describe what you want to learn next about AI agents. Here you would like to put something realistically. For example, I want to get good at building production-ready multi-agent workflows with CrewAI. Let's hit enter and see the preference researcher agent start working. While it is running, it may ask a couple of follow-up questions, then generate a structured summary of your goals and constraints. That summary is stored into long-term memory and associated with this crew and this user. Next, the learning planner agent runs. It reads from the memory stack, combines that information with the user profile knowledge source, and produces a 3-step plan tailored to your preferences. You will see something like this when the agents are done running. You can see the final output of the 2 agents, and you can also see it in the MD file. Here on the left, you can also see where the CrewAI stored the long-term and the short-term memory. Now the preference researcher already has a history of your previous goals in long-term memory. It can build on that instead of starting from zero. The learning planner will see both your original goals and this new focus, plus your user profile knowledge. And it should generate a plan that acknowledges what you have already done and what you want next. Each run will also append a new learning plan to learningplan.md if you decide to extend the script, or you can choose to version that file as part of your own workflow. Let's zoom back out and connect the dots. We started with the default pattern, a stateless LLM wrapped in some glue code that forgets everything between calls. Then we introduced a more realistic mental model, short-term memory for the current run, long-term memory for distilled outcomes, and a knowledge layer for stable facts, all accessed via vector-based recall. We mapped that model directly into CrewAI primitives. We used memory equals true to activate short-term and long-term memory, entity memory for tracking specific actors, and explicit knowledge sources for declarative context. On top of that, we built a small 2-agent crew that actually learns your preferences across runs instead of starting from zero every time. From here you can swap the domain. Customers instead of learners, incidents instead of sessions, architecture decisions instead of learning plans. The pattern stays the same, design for episodic versus declarative memory, and decide deliberately what gets promoted into long-term storage. If you want to keep going deeper into CrewAI, multi-agent patterns, and real-world LLM systems, subscribe to ByteBuilder and follow the CrewAI and Agent System series. We will keep moving from understanding to implementation, one concept, one system, one builder at a time.